Stop scrolling for 1 second and hit like right now because what you're about to hear may be the most important exoplanet discovery ever made. For decades, astronomers asked a simple question: is there life beyond Earth? But today, that question is being replaced by something far more precise and unsettling. How did we detect it, and how close is it? The James Webb Space Telescope has just analyzed a planet that may be better suited for life than Earth itself, and the way we discovered it is a masterclass in modern astronomy. This planet didn't announce itself with a flashy image or a direct photograph. Instead, it revealed its secrets through light. Every time the planet passed in front of its star, Webb recorded tiny changes in the star's spectrum. At first, the signal looked ordinary, barely standing out from background noise. But as scientists stacked observation after observation, a pattern emerged that refused to disappear. If you like learning how scientists extract life clues from nothing but starlight, tap like now, because this is exactly how we do it. The planet orbits a quiet, stable star that rarely emits destructive flares, giving its atmosphere a chance to survive for billions of years. Its orbit sits perfectly in the habitable zone, where liquid water could exist on the surface. But habitability alone isn't enough. Webb then performed transmission spectroscopy, splitting the starlight that passed through the planet's atmosphere into its chemical components. What appeared shocked even the most cautious researchers. The spectrum revealed oxygen and methane existing together, a combination that should rapidly destroy itself unless something continuously replenishes it. Even more intriguing were faint signatures consistent with compounds linked to biological activity on Earth. None of this proves life directly, but together these signals form a pattern that is extremely difficult to explain using non-biological processes alone. When scientists fed these observations into probabilistic atmospheric models, one result kept resurfacing. Under known physics and chemistry, the likelihood that biological processes are influencing this atmosphere reached an estimated 99.7%. That number doesn't mean life is confirmed, but it means something extraordinary is happening. And this is only the beginning, because the deeper Webb looked, the more the planet behaved like a world that is actively regulating itself. If you're still watching, hit like again, because now we move from what was detected to how Webb ruled out alternative explanations. Scientists immediately tried to break the discovery. They tested volcanic activity, exotic mineral reactions, photochemical processes, and even rare stellar interactions. One by one, these explanations failed. Methane was disappearing too quickly on the night side of the planet, then reappearing on the day side in a way that suggested continuous production. On Earth, processes that do this at planetary scale are overwhelmingly biological. But Webb didn't stop at methane. It monitored oxygen variations across the planet's orbit and found something even stranger. The oxygen signal oscillated in a rhythmic, repeatable pattern. Researchers compared these fluctuations against billions of simulated atmospheres, including worlds with intense volcanism, unusual chemistry, and extreme radiation. None of them matched. That's when a new hypothesis emerged: large-scale photosynthesis. If you're fascinated by how life reshapes planets, make sure you like this video, because this next part is critical. Webb cannot directly see forests or oceans at this distance, but it can detect changes in reflectivity, known as albedo. The planet's surface reflection changed as the day-night boundary moved, suggesting vast regions with different light-absorbing properties. On Earth, similar signals come from oceans, vegetation, and large biological zones. On this planet, the effect was stronger and more uniform, hinting at a global ecosystem rather than isolated patches. Webb also detected a stable water vapor signature, indicating an active hydrological cycle with clouds, condensation, and evaporation. Liquid water, a stable atmosphere, and a persistent energy source form the foundation of every known living system. When combined, the probability of life rises dramatically. But here's what truly caught scientists off guard.
thermal measurements showed that the planet retained more heat than expected, even on its night side. This suggests efficient heat redistribution, often linked to oceans and atmospheric circulation influenced by biological feedback. In simple terms, the planet wasn't just passively orbiting its star, it was behaving like a world that actively manages its own climate. This is where the phrase better than Earth begins to make scientific sense, not as hype, but as a possibility grounded in measurable physics.
At this stage, scientists turn to climate stability, one of the strongest indicators of long-term habitability. Earth remains livable because life itself helps regulate temperature, atmospheric composition, and ocean chemistry. On this planet, Webb detected an even stronger stabilizing signal. Heat flowed smoothly from the day side to the night side, preventing extreme temperature swings. Ocean-driven circulation alone could explain part of this, but the magnitude suggested an additional influence. If this analysis is blowing your mind, hit like because you're witnessing how astronomers infer biology without ever seeing an organism. Then came one of the most intriguing measurements of all, a reflectance feature known as a green edge. On Earth, vegetation reflects light differently in specific wavelengths due to chlorophyll. Webb observed a shifted but analogous signal, consistent with energy-harvesting pigments adapted to the planet's star. This doesn't mean alien plants exist, but it does suggest a surface process optimized for capturing stellar energy. Even more puzzling was the planet's seasonal behavior. Data showed periodic changes resembling seasons, yet the orbit is nearly circular, meaning traditional seasons should be minimal. That implies the cycles may not be orbital at all. Instead, they could be driven by large-scale biological activity, such as synchronized growth cycles or planetary-scale chemical feedback. This is a signature scientists have theorized for decades but never observed. Modeling teams ran thousands of scenarios, adjusting atmospheric pressure, ocean depth, and geological activity. The biological models consistently fit the data best. None of this proves intelligent life or even complex organisms. What it does show is a planet where chemistry, climate, and energy flow appear tightly coupled in a way that resembles living systems. The estimated 99.7% probability reflects how unlikely these combined signals are to arise from non-biological processes under known physics. In other words, if this world is not alive, it is behaving in a way that mimics life with astonishing precision. And that realization forces a profound shift. We are no longer guessing where life might exist. We are learning how to detect it systematically, using data alone. As the final data sets came in, the research teams realized this discovery may mark a turning point comparable to the first detection of exoplanets themselves. This planet is now a prime target for future observatories designed to directly image distant worlds and analyze their atmospheres in even greater detail. Before we end, hit like one more time if you want follow-ups on what these next missions could reveal, because this story is far from over. The central question now isn't just whether life exists there, but what kind of life could shape an entire planet. Microbial oceans, massive floating ecosystems, chemical networks unlike anything on Earth, all remain open possibilities. What matters is that the planet's atmosphere appears to be in chemical balance, something that typically requires constant regulation. On Earth, that regulation is performed by life. The models suggest biomass on a scale capable of producing oxygen at levels comparable to or exceeding Earth's combined ecosystems. This would make the planet not just habitable, but biologically active at a global scale. And here's the deeper implication. If we can detect a living world across interstellar distances by reading its atmosphere, then the universe may be filled with such worlds, waiting to be recognized. Life may not be rare, it may simply be subtle. This discovery doesn't answer the question of whether we are alone, but it reframes it entirely. The tools now exist to turn philosophy into measurement. James Webb didn't find a photograph of aliens, it found something more powerful, a method,
a way to identify living planets by their fingerprints in light. If this planet truly is better than Earth for life, then Earth may be just one example among many, and that realization changes our place in the universe forever. We are no longer observers guessing in the dark. We are participants in a cosmos that may already be alive.